This was another test in San Jose, and this has 100 samples. So every line is 100 seconds for the total of 5 minutes. Here you will see the blue line because it's 5 minutes. They're compressed together. There is something going on in the background. No other instrument can show such a thing, that there is CDMA or whatever is going in the background, and it is affecting GPS within the band. Probably more than 1 dB that we were all so much worried about light squared already exists within our cities with this level. I'll show you more what exists already. This is GPS L2. It's almost clean. GPS L5, almost clean, but still we have variations in AGC, 1.7 dB variations. Anything above 1 dB, I will mark it with red. Similarly for San Jose 2, and here is GLONASS L2 in San Jose. It doesn't have, that's what I mean in here. You don't see any effect on the performance or anything because our receiver compensates for it with a 60 megahertz sampling of 8 bits and closing the AGC at 100 kilohertz and providing 60 megahertz of 8-bit to 3-bit conversion. We cover for this, but these are things that they shouldn't exist in our band, and they do exist. And look, again, this is 100 samples, means everyone is 10 seconds, it's 100 seconds. So this is a pattern that exists within our GPS bands today in San Jose, in the heart of Silicon Valley. And this is the other information about that I said after digital processing. You see we have lots of green numbers. So we are affected by more than 3 dB already. And this is the polar plot, and this is the summary. 1.2 dB variations here, 1.7 here, 2.2, GPS L1, GPS L2, and GLONASS L2. Now, we had similar thing in Moscow. If you see here, it doesn't go all the way down because it was set to 50 kilohertz sampling, so we cover about 25 megahertz band. But it will tell the story. GPS L1 gets affected, these numbers, because there were some external cable involved. So don't pay too much attention to these average numbers. We should have calibrated this. System looks clean. You see, this is the CA code that stands out even in the raw RF spectrum, and everything is clean. This is GPS L2. It's pretty bad. It's in the center of Moscow. Look at the shape. GPS L5, it's kind of okay. GLONASS L1, kind of okay. GLONASS L2, it's pretty bad. We cannot track it. We were not able to track GLONASS L2 within Moscow. And this shows the after digital part. These are GPS numbers that are mostly red, and GLONASS numbers on the P2, they're all gone. In the center of Moscow, we were not able to track GLONASS, and there was not one day. This is the polar plot. I will go through this because there were several tests. I will just go through them fast to see this is the repeated thing was happening day over and day. Okay, this is day number 2 or another day. GPS L2, GPS L5, GLONASS L1, GLONASS L2 again, and all the GLONASS signals are out. People that were doing survey in the center of Moscow had no clue that they were not using GLONASS at all, because CA code was there, and they were getting answers. We were using GPS GLONASS. And the signals were there because they all look at the existence of a satellite by looking at the CA code only. CA code tracks, everything is okay. There was, for navigation is okay, but high precision users in the center of Moscow, they were not able to use their own satellites for doing any high precision receivers. So this was Moscow 2, Moscow 3, I will go through it again. It affects GPS L2 also because GPS L2 and GLONASS L2 are near each other. This was day number 3. Again, GLONASS L2. The same, look, there is no information on L2 from GLONASS satellites. So, same summary. Now I will show you only GLONASS L2 in several days. This is day 4. This is day 5, and these are all 10 samples each. This is 50 samples. That's why you see the pictures are more crisp. The variations of 15 dB going up and down, and no track of GLONASS satellites. Again, day 7, or another day of GLONASS L2. So this, I called my good friend Sergei Revnivov sitting here, and Sergei, I said, Sergei, this is the problem that you have in Moscow, and he didn't know, and he told me what to do. We invited ministries of communication and the head of Moscow Roscosmos, Sergei, Russian Space Agency General Shilov and all, and they were pretty shocked. And they have authorized everything anybody can do to find who is doing this. And this, we did it on last week, September 12, around 2 o'clock in our office. This is what I say, such a tool never existed, and this is something that exists in every unit, in the small things that you have in your hand. As Michael is going to demonstrate today, we can connect any of the receiver to anyone, any of our controllers, to anywhere in the world, and show the stuff that I was reporting to you today. These are all not artistic, artworks. These are screenshots from exact receivers that you're going to see today. Now, we have gone one step more. We want to look at the heartbeat of the patient for high precision users. What is the heartbeat? What do we measure? Garmin uses code face. No problem. They have accuracy of many meters, and they talk about many meters of error, but we talk about millimeter. Why? Because we track the phase of the carrier. This is the artist rendition of the carrier, and when we lock in here, lock point moves around here. This is when the heartbeat is okay. If we have a little bit more interference, this may jump from this lock point to this jump, to this. This absolutely no one can notice, has no effect on low precision receivers. But this, being about 10 centimeters of error, will give the high precision users 10, 20, 30 centimeters of error without noticing. Of course, this can be discovered in post-processing software and in some enhanced RTK engines. But it's too late after you say, oh, I had cycle slips. We do this cycle slip as a measure of looking how good the receiver is and how clean the environment is. That is like looking at the heartbeat of the receiver, and you say, what happened? And you can track it for 1 week or as what you want, and you say, during this period, how many cycle slips I had? or this patient had missed the heartbeat how many times during the past several hours or days or whatever.